Okay, in this video we are going to see how every row operation can be viewed as a multiplication on the left by a special matrix. That means that if we start with a matrix and we do a row operation to get matrix B, then B can be viewed as a special matrix, let's call it F times A. And every row operation comes with a special matrix F. These F are going to be denoted like EIJ or EIJ alpha or EI alpha. Okay, before continuing, let me just say something about the notation. When we write E sub I and we are thinking about a vector in Rn, if we think of this as a column vector, then we're going to be thinking about the vector 0, 0, a 1, a 0, and a 0. A vector that has zeros everywhere, but in the ith entry. And if we think about the E sub I as a row vector, then we're going to think about this vector. Either like this, with a 1 here, and this is the ith entry, or sometimes like this, like 0, 0, 1, 0, 0, where this is the ith entry. This is like the view as a 1 by n matrix. Then, just as an example, if I say E sub 2, and we are thinking as a vector in R3, and we are thinking about a column vector, then I'm thinking about this vector. And if I am thinking about a row vector, then I'm thinking about either this or like a matrix like this. Okay, now we are ready to proceed. Let's see each one of the row operations. Let's suppose that we have the matrix A. Let's just do 1, 2, 3, negative 1, 2, 1, 0, 1, 4. Right? And let's suppose that the matrix B is obtained by changing row 2 and row 3. Then, in this case, we get the matrix 1, 2, 3, 0, 1, 4, negative 1, 2, 1. The observation is that this matrix B is the same matrix. You can get B by multiplying A by the matrix E2, 3, where the matrix A2, 3 is the matrix with rows. In the first row is the E1. In the second row, you put E sub 3 because 2 and 3 are interchanged. And in the third row, you write down E sub 2. Let's see what is this matrix. We have E sub 1, 1, 0, 0, E sub 3, 0, 0, 1, and E sub 2, 0, 1, 0. Let's check that this is true. If I multiply the matrix 1, 0, 0, 0, 0, 1, 0, 1, 0 times the matrix 1, 2, 3, negative 1, 2, 1, 0, 1, 4, then we get the matrix entry 1, 1 is 1 times 1 plus 0 is 1. Entry 1, 2, 2 plus 0 is 2. Entry 1, 3, 3 plus 0 is 3. Entry 2, 1. I multiply this row with this column, and then I get 0 plus 0 is 0. This entry, this product of this row with this entry, 0 plus 1 is 1. And here you get 4. And then when you get this entry, 3, 1, third row, first column, 0 plus negative 1 plus 0 is negative 1, and then you get 2 and then you get 1. Then that's the observation that this row operation can be viewed as a left multiplication of this matrix with the matrix A, where this matrix is denoted by E23. Notice that E23 and E32 are the same thing. In general, we have that this is going to happen. If you have a matrix n by n, and you get the matrix B using the change R, by changing the row Ri and Rj, then the matrix B is equal to the matrix Eij times A, where Eij is the matrix whose rows are E1. Let's think about here, this is the ith entry, and let's suppose that this is the jth entry, and then everything is the same, but in here, in the ith entry, you write down the vector e sub j, and in the jth entry, you write the vector e sub I. The kth entry is just the vector e sub k, if k is different from I and j. Then this is the matrix that makes that change. As an example, if we have the matrix E23, like the 5 by 5 matrix, then this matrix is the matrix. The first entry is just the vector e sub 1, which is 1, 0, 0, 0, 0. The second ones, 2 and 3 are interchanged, then the second one is e sub 3. The third row is going to be the vector e sub 2. The fourth row is just e sub 4. And the fifth row is just the vector e sub 5. We have that the first row is e sub 1, the fourth row is e sub 4, the fifth row is e sub 5, and the only rows that are interchanged are e sub 2 and e sub 3. In the second row, you write down the vector e sub 3, and in the third row, you write down the vector e sub 2. Okay, this is in regard with this row operation. Let's try to do another row operation and see what is the right matrix to multiply it on the left. Let's keep this. Let's suppose that we're going to do the operation 3 times row 3, or let's say 3 times row 2. Then what matrix do we get? 1, 2, 3, negative 3, 6, 3, 0, 1, 4. The observation is that if this is the matrix B, then this matrix B is the same as the matrix A times the matrix E sub 2, 3. But where this E sub 2, 3 is the matrix that has, in the first row, it has the vector E1. In the second row, it has the vector 3 times E2. And in the third row, it has the vector E3. And then if we multiply this by this matrix, 1, 2, 3, negative 1, 2, 1, 0, 1, 4, then we get the matrix 1, 2, 3. When you multiply this by this, you get 0 minus 3 plus 0 is negative 3, 0 plus 6 plus 0 is 6, and then 3, and then 0, 1, 4, which is the matrix B. And in general, what we have is that if we get the matrix B by doing the operation alpha times Ri, where alpha is different from 0. Then the matrix B is just the matrix A times the matrix EI alpha, where the matrix EI alpha is the matrix in the first row is the vector E1, or let's say that this is the ith row, and in the kth row is just E sub k, but in the ith row you have alpha times E sub I, and then here is just E sub n. Then as an example, let me do an example here. If you have E 4 square root of 2 in a matrix 4 by 4, then this matrix is, in the first row you write the vector E1. In the second row you write the vector E2. In the third row you write the vector E3. And in the fourth row you write the vector square root of 2 times E4, which is the vector 0, 0, 0, square root of 2. Then this is the matrix E4 square root of 2. Okay, let's do the final row operation that can be done on a matrix, and is a row operation of this type. Let's suppose that we decide to do to add to row 2, we decide to add 2 times row 1. We're going to change this row by adding 2 times this row. Then what do we get? Third row stays the same. The first row stays the same. And in the second row, we just add twice the first row. Then we get 1. Then we get 2 times 2 is 4 plus 2 is 6. 2 times 3 is 6 plus 1 is 7. If this is the matrix B, then this matrix B is just equal to a matrix that we are going to denote by E sub 2, 1, and then the 2. The 2 is because the row 2 is the one that is changing. The 1 is because you are adding a multiple of row 1, and this is the multiple, times the matrix A. In this case, this matrix is just the matrix. The first row is not changing, then you just write E1. The second row is changing, then for the second row, this is the row that is changing, you write E sub 2 plus 2 times E1. Let's see, this is the matrix, this is the vector 2, 1, 0. Remember, this is the vector 0, 1, 0 plus 2, 0, 1. And when you do this, you get this vector. And here, E3 is just the vector E3. Then when I multiply it by A, 1, 2, 3, negative 1, 2, 1, 0, 1, 4, we get the matrix 1, 2, 3. For this entry here, we do this row times this, and they have 2 plus negative 1 is just 1 plus 0. And here we have 2 times 2 is 4 plus 2 is 6. And here 2 times 3 is 6 plus 1 is 7 plus 0 is just 7. And here we have 0 plus 0 plus 0 is 0. 0 plus 0 plus 1 is 1. And here we have 0 plus 0 plus 4 is 4, which is the same matrix B. In general, what we have is that if we, let me erase this. if we obtain the matrix B by doing this row operation, changing row I by adding to it alpha times row J, then the matrix B is just the matrix E I J alpha, this is the row that is changing, times the matrix A, and this is it has to do with the factor, where this matrix E I J alpha, the only row that is going to change is the ith row. All the other rows are going to be just the same row as the identity. Then this row is going to change by EI plus alpha times EJ, and all the other rows are just, the first row is E1 and the last row is En. As an example, if we have the matrix E2, 4, pi for a 6 by 6 matrix, then this matrix is going to be, the only row that is going to change is the second row. And the first row is just E1. 1, 2, 3, 4, 5, 6. The second row is going to be the vector E2 plus pi times E4. This is the vector 0, 1, 0, pi, 0, 0. And this is 0, 1, 0, pi, 0, 0. And all the other rows are going to be the same rows as the identity matrix. Here we have 0, 0, 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 1, 0. Let me erase this. And the last row is going to be 0, 0, 0, 0, 0, 1. Then this is the matrix E to 4 pi in the set of 6 by 6 matrices. Then these are the three results. If you get the matrix B by doing the row operation of changing two rows of the matrix A, then essentially the matrix B is what you get when you multiply on the left the matrix A by this matrix that is defined in this form. If you get the matrix B by multiplying by alpha, with that alpha different from 0, one of the rows, then that's the same as multiplying by A on the left with this matrix, and then you get the same B. And finally, if you get the matrix B by doing this type of operation by adding to row I alpha times row J, then the matrix B can be obtained by multiplying on the left this matrix to the matrix A, where this matrix is like this. I think it's a good idea to remind you how the determinant changes when you get this. Here the determinant of B is just negative the determinant of A. Here the determinant of B, in this case the determinant of B is just alpha times the determinant of A, and here the determinant of B is equal to the determinant of A. And maybe it's good to point out that the determinant of this type of matrix, the determinant of this type of matrix, E, and let's say IJ alpha, this determinant is just 1. Let me just check one particular example. If you have the matrix like E1, 3, 5. Then what matrix is this? This is the matrix, the only row that is different is row 3, and row 3 is going to be E3 plus 5 times E1, which is 5, 0, 1. The second row is going to be this, and the first row is going to be 1, 0, 0. Therefore, we have that to compute the determinant, we can use this row, and then it will be 1 times this determinant, 1, 0, 0, 1, and then plus 0 times 1 determinant, plus 0 times 1 determinant, and this is the determinant of 1. Therefore, here we have checked the property, we have this, that the determinant of Eij alpha times A, which is the determinant of B, is just the determinant of Eij alpha, because in this case this is 1, times the determinant of A. Then we have checked that in this particular case, the determinant of a product is the product of the determinant of the matrices. In the same way that we show that the determinant of this product of these two matrices is the determinant, is the product of the determinants, we can show that the determinant of a matrix like this, right? Like this matrix times A is just the determinant of Eij times the determinant of A. And the reason is because easily we can see that this determinant is -1, and when you apply this row operation, the determinant of this matrix is just negative the determinant of this matrix. Also, we can show that the determinant of Ei alpha times A is equal to the determinant of Ei alpha times the determinant of A. And the reason is because the determinant of this matrix, Ei alpha, is just alpha, and when you get this matrix, then essentially you're multiplying a row by alpha, then the determinant changes by just alpha times the determinant. And these are easy properties to show, and with these properties we are going to show that the determinant of A times B is equal to the determinant of A times the determinant of B. Maybe just to get familiar to what I'm talking about, let's see an easy example. Let's suppose that A is 2, 1, negative 1, 1, and B is 2, 0, 1, 7, right? Then in this case, the determinant of A is 2 minus negative 1 is 3, and this determinant, the determinant of B, is 14. Now let's do A times B. A times B is 2, 1, negative 1, 1 times 2, 0, 1, 7. And this is the matrix 2 times 2 is 4 plus 1 is 5. 2 times 0 is 0 plus 7 is 7. Negative 2 plus 1 is negative 1. And 0 plus 1 is 7. Then this is the matrix AB, and what is the determinant of A times B? It will be 35 minus negative 7, which is equal to 42. And then the question is 3 times 14 equal to 42? And that's correct. Okay, this was just an example of a 2 by 2 matrix, but in general this is true for every n by n matrix. And then the idea of the proof is as follows. First, we notice that C is singular. If and only if the determinant of C is equal to 0. And we have shown that. Also, we know that if A or B are singular, then A times B is also singular. And how do we show this? If B is singular, let me just say it. If B is singular, that means that the null of B is different from the vector 0. That means that we can find a vector B different from the 0 vector such that B times V is the 0 vector. But then what happens if we do A times B, the vector V? Then this will be A times B times the vector V, and this is A times the 0 vector, and this is the 0 vector. That means that A times B is singular because we can find a non-zero vector such that the product of this matrix with that vector produces the 0 vector. Let's do the other argument. If A is singular, what happens if A is singular? If A is singular, that means that I can find a vector B different from the 0 vector such that A times V is the 0 vector. But then what do we have? We have either that B is singular or B is not singular. We want to show that A times B is singular. If B is singular, we already know that the whole product is singular. Then let's suppose that B is not singular. But then if B is not singular, we know that we can find a vector W such that B times W is the vector B. And then when we do A times B times W, we get that this is equal to A times BW, and then this is A times V, but A times V is 0. Then we have that if one of the two matrices is singular, then definitely the product is also singular. We have this result. And then using this result, we know that if A or B are singular, then this is true, because if A or B are singular, then the right hand side is 0 and the left hand side is 0 because of this theorem. But then we can assume that both of them are not singular. Then we can assume that A and B are non-singular. That means that A is row equivalent to the identity matrix. That means that we can do row reduction to get the identity matrix, and that means that we can get the identity matrix A after a sequence of products with this type of matrices. Let's call it E1, E2, and EK, where each one of these, each E sub I, is either EIJ or EIJ alpha or EI alpha. Then we have that this is true. But because of this property, that the determinant of a product of one of these matrices times the matrix A is the determinant of this product is the product of the determinants, then we know that we have this identity. The determinant of EK times the determinant of ek minus 1 times the determinant of E1 times the determinant of A is equal to the determinant of the identity matrix, which is 1. From here we get that the determinant of A is just equal to 1 over this whole determinants. Determinant of E1 times the determinant of EK. But now let's think about A times B. Right? We know that the determinant of this matrix EK times EK minus 1 times E2 times E1 times AB, this is the determinant of EK times the determinant of E1 times the determinant of A times B. Right? So just notice, let me organize this. This is just the determinant of A. And we now know that this determinant, this is the determinant of A times B. But let's see what is this. This product here is just the identity matrix. That means that this is the determinant of the identity matrix times B. It's just this determinant, the determinant of EK times the determinant of E1 times the determinant of A times B. But the identity times the matrix B is just the matrix B, and this is the determinant of B. But then from here, what do I get? I get that if, when I solve for the determinant of AB, A times B, this is equal to the determinant of B over these numbers, determinant of EK times the determinant of E1, and this is just, using this identity, this is just the determinant of A times the determinant of B.